let's recall we last week about the colligative property. The colligative property is that like if you have uh, solid materials and you put the solid material into the liquid and solid material dissolved in the liquid, so this will affect the vapor pressure and the boiling point of the liquid, and also freezing point of the liquid, and also osmotic pressure. But this is not, we are going to talk about this today. So this will affect three properties of the liquid. And what we call is about this phenomena is colligative, colligative solution properties. So relatively, it will lower the vapor pressure, and you will make the boiling point higher, and you will make the freezing point of the liquid lower. And we already discussed about this, and we already talked about the application of these properties. So today, we are going to do the calculation about these properties. Okay? So colligative property calculation is that, when we measure, we have a measure value, and we understand we will lower the vapor pressure, and we will higher the boiling point and lower the freezing point. But what's the degree of this? And then because we need to know the differences. So as I just told you, the relationship of the vapor pressure and the concentration of solute. So you put how many solute you put, how many salt or sugar you put will affect the vapor pressure, boiling point, and freezing point. And what's the degree it will affect it. So that's what we are going to know. So the main to do here, we are going to talk is concentration. So the measure value of the colligative property solution is that we understand, actually this is very complicated, but we don't want to make this so complicated when you are in the first year. So we use a simple case to let you understand this. So that's why we make some conditions here. The first one, in order to have this calculation, we need to know that we want to use the non-volatile materials, like this material into this liquid, this solid material into this liquid. This material need to be non-volatile. It cannot vaporize to become gas phase, into the gas phase. And also, this material is not reactive with the solvent, with the liquid. No, it cannot. Okay, this is the condition. And also, this material cannot dissolve, cannot dissociative in this solvent. That means what? You cannot use salt. Salt is not in the case for this calculation, because the salt, if we put salt into water, salt will become sodium cation and chlorine anion. But this is non-dissociative, right? So if we put sugar in, yes, sugar can apply in this case, because sugar is not going to dissociate, okay, in the water. Okay, so what we want to know is, we want to know how many sugar we put into this liquid, and then what's the degree, how many vapor pressure will be lower. Okay, what's the degree of the boiling point will increase, what's the degree of freezing point will decrease. Okay, so this is what we want to know. So let's talk about, in the very beginning, the solvent vapor pressure. Let's assume this solvent is water, and we have the concentration of the fraction, I should say, the fraction of the water in this liquid, in this solvent, is x sub s. Okay, and then the solute, like, let's make an example, like sugar. If we put sugar into this water, and we can use x is the molar fraction of the sugar in the water. Okay, and then under different temperature and the pressure, we will get the different vapor pressure of the water and the molar fraction of the water, right? That's what we practiced last week and the week before last week. So we want to know the molar fraction of water, and we want to know the partial pressure of the water. in the gas phase. Okay, and here we use S, PS. S stand for solvent. Okay, X stand for if there's no if there's no subscription, and this X is regarded as a solute. Okay, so according to Law's law, we understand Pi equal to Yi capital P equal to Xi Pi star function of T. That's what we know. This is Law's law. And then partial pressure solution, partial pressure of the solvent. This one, if we only think of, there are only two species in the liquid phase. One is water, one is sugar, for example. So you can modify this equation like this. Like PS is the solvent, right? The partial pressure of the solvent at the function of T equal to PYS. S stands for solvent. Capital P equal to PS times PS star function of T. As you can see, we just replace A to become S. That's it. However, in the following sentence, in the following equation, you will know that because PS equal to 1 minus X, if we only have two species, and X sub S plus X equal to 1, right? Because we only have two species. So this one will, X sub S will replace to 1 minus X. It becomes like this. Okay? So it depends on how many amount of the sugar you put into the water. You will change the what? You will change the partial pressure. Okay? So if X is equal to 0, if I don't have any sugar into the water, so X is equal to 0. So X sub S will be equal to 1. That means what? That means this one will be equal to this one, because this is 0, right? So PS function of T will become what? PS star function of T. So what is PS star function of T? The saturated vapor pressure as a pure component, right? Okay, so this is the one apply. So if solute is non-volatile and the vapor phase only solvent, and in this case, here we just talk about only two species in the liquid phase, and this condition we call effective solvent vapor pressure. So this solute doesn't vaporize. So, and especially this is a special case we call effective solvent vapor pressure. Okay? Right. So in this case, we rewrite this equation. Like if X equals to 0, this is pure solvent, right? We just mentioned this before. And if solvent is non-volatile, we call this effective vapor pressure, right? Effective solvent vapor pressure. So we use this PS star blanket function sub E. E stands for effective. Okay? So PS star function of E, sub E equal to this. So see that? We just change this equation and we use E here. We use E here. Okay, so this is easier for you to understand. E is called effective, and we are talking about only two species. And also the solute doesn't vaporize. So because you understand, this is always less than 1. Why? Because X sub S plus X equal to 1, right? So 1 minus X will be always less than 1. So we understand effective vapor is all the time less than saturated vapor, unless X is equal to 0, right? Okay, so effective solvent vapor pressure is always less than the vapor pressure of the pure solvent. Okay. Right, so let's now think of if I put sugar into the solvent, and what the vapor pressure will be. And that's what we call vapor pressure lowering. we call delta PS. So what's the degree of lowering? So let's say that this is effective solvent vapor pressure here, and then it's always less than vapor pressure of pure solvent. That's what we know before, right? So what's the vapor pressure lowering? Is that delta PS will be equal to PS star. This is what? This is the vapor pressure without solute, right? Okay, vapor pressure without solute. And minus what? This is the vapor pressure with solute. Okay, this vapor pressure with solute. So if we know that this is equal to this one, and we replace this to here, then what have we got? What have we got? The delta PS star will be x times PS star. So what does that mean? The degree increase will be the function of x. Okay? So the more sugar I put into the water, the much lower vapor pressure I will have. So this delta PS will be function of x. Okay, ladies and gentlemen, please remember this one. Delta PS star equal to x PS star. Okay, so you need to remember this. Okay, so I give you an example. If a solution contains 20% more solute, that means x equal to 0.2. That means what? The delta PS will be what? Will be 0.2 PS. Right? What does that mean? Delta PS will be 0.2 PS. Is that the solvent partial pressure is about 80% because you lower 20%, right? So the partial pressure is about 80%. For example, if you have water, the vapor pressure is 760 millimeter mercury, and you have 20% sugar into the water. So what's the vapor pressure of the water if you have sugar in the water? 760 times what? Times 80%, right? Times 80%, because you lower 20%. Okay, so the vapor pressure of the pure solvent at a constant temperature, regardless the temperature, the pressure, and what the solute and the solvent are. So this equation very clearly tells us that if you follow this equation, it doesn't matter the temperature or pressure or what is the solute, because it doesn't matter only the concentration, the molar fraction of the solute only. Okay, it can be sugar, it can be whatever can dissolve in the solvent. Okay, so now we understand if we have this is a phase diagram of water. As you know, this is the original curve here. The original curve here is pure solvent. Let's regard this as a water. Okay, so and then you start to put sugar into this solvent, and then this is solution, right? So you put sugar into this solution, solvent, it becomes solution. So the boiling point will be high. Let's say this P0 is 1 atm. So this the boiling point will be higher. The melting point or the freezing point will be lower, right? Because this is what? This is solid phase, this is liquid phase, and this is gas phase. So what we are talking here is from liquid to gas, what we call a boiling point, right? From liquid to solid, now what we call is freezing point or melting point. So you are increasing the boiling point, you are decreasing the freezing point. So what's the degree of this? And it related to the amount of the sugar you put. So this is boiling point, so original boiling point without sugar, right? Without solute. And this is the boiling point with solute. And this is melting point only, solvent only. And this is melting point. This is with solute. Okay? And if I want to tell you, if I put the sugar more compared to this dash line here, if I have a high concentration of solute, so where is the curve? Can you draw a curve for me? It will become like this. The more sugar you put, the higher boiling point you will have, the lower melting point you will have. And if you put more, higher, much higher, the curve will become like this. And this is delta, right? This is delta. So what's the degree of this? So this is what we call the phase equilibrium curve for pure solvent as solution. Is that this is delta TB and this is delta TM. B stands for boiling, right? M stands for melting. So the lower of the solvent vapor pressure has two important consequences. Solvent at a given pressure is the boiling at a higher temperature and also the freezing at the lower temperature than a pure solvent. That's what we are going to talk. We already talked the phenomena with you last week, and we want to use mathematics method to calculate what's the degree of this lowering and higher lowering. And we also know the higher solute concentration, the greater separation between the pure solvent and the solution curve, right? Delta PS. And if you have higher fraction, molar fraction, you will have higher separation between the original curve and the curve after you put the solvent in, after you put the solute in. Right, ladies and gentlemen, this is the boiling point elevation, okay, for a dilute solution. So now we want to calculate this delta TB here. Delta TB, what's the degree of this TB? Delta TB. So according to Clausius-Clipperton equation, I hope you still remember this. This is called Clausius-Clipperton equation. And you know what? You know delta P, right? Do you know what is delta H sub V? This is what we call latent heat, right? Latent heat. And especially this latent heat is in the gas from liquid phase to vapor phase. Gas constant temperature, B is what? B is the gas constant. Sorry, B is the constant. So this is what we call Clausius-Clipperton equation. And this is what? Modified Law's law, right? Modified Law's law. Okay? So for the pure solvent, we have this. This is equation 1. So we use this pure solvent here. TB sub 0 is temperature here and PS. So this is easy to understand because this is a Clausius-Clipperton equation. But if we have solution, if we put the sugar into the water, we can have another Clausius-Clipperton equation. Let's say TBS, because you increase the temperature, the temperature will be different, right? So you have this. This is another equation. This is equation 1 and equation 2. And then you have equation 1 minus equation 2. Can you do that? Equation 1 minus equation 2, that will be like this. I don't have time to write this to you, but I hope you can understand and you can quickly pick up what I'm trying to say to you. So this minus this and this minus this, right? So you have equal the symbol equal symbol here, left side, and the equal symbol here, right side. Right. So according to, because this is called dilute solution. Dilute solution means the X is not much. It's not very heavy. So if X is not that heavy, you understand this delta HV1 will be almost equal to delta HV2. Because latent heat, it doesn't change much. Okay? And then so let's rearrange this equation on the right side. On the right side here. So if you take it, if this 2 doesn't change much, so you can regard this 2 as a 1. So you move this out, delta H out, to become like this. And then if and we also know if we rearrange this temperature T0 times T sub S, it will be equal to very similar to T0 power 2. So if you do this and we rearrange this again, and it will become like this. So we don't change anything on the left hand side. We just change this here. Okay? Right, and then let's start to modify the equation on the left hand side. So this one, we understand PS function of TB will be equal to x1 minus x P0 here. Why is this? I hope you still remember I told you this is what we call modified, right? Modified Gauss law, because you don't have solute and solvent into the solution, in a solution. So this can change, this one can change to this one. So if you put this one into here, and then this is natural log, right? Natural log minus natural log, you can put these two, rearrange these two together into this equation. And eventually you will get minus x here. This one can rearrange it to can change it to minus x. So it becomes this one. If you don't understand, go home, do some practice. I'm sure you will understand. Or ask your friend. This is a very easy, simple calculation. Okay, so once you rearrange the things on the right hand side, left hand side and right hand side, and then now you get this. Okay, and then again you rearrange this equation, become like this. You just leave the delta, you just leave the TBS minus TB0 here on the right hand side, and you move others to the left hand side. Okay, and do you find out something here? Do you find out something here? Yes, you do, because TBS minus TB0 is here, right? That's why we call delta TB. So again, rearrange. We call this one here is delta TB equal to what? Equal to this one. So what does this equation tell you? What's the information you have got here? The delta TB is related to what? The concentration of the solute. Okay, the molar fraction of the solute in the water or in the solvent. Okay, you can say the molar fraction of sugar in the water. Okay, and this is you can measure the temperature in original temperature, right? The TB0 is the original temperature before you put the sugar in. Gas constant. And why is this? This is latent heat of water. You can check from the table. Okay, you can do the calculation according to Clausius-Krypton equation and the Krypton equation. It doesn't bother you at all. Okay, so what you understand here is that if you know this equation, you understand delta B is related to the amount of the sugar you put in the water only. Okay, right. So this equation, what I want to tell you is, in your final exam, I will give you this equation, but I don't tell you the definition of this. What is delta H? What is X? What is TB0? You need to understand. You need to understand the definition, okay? So what we understand, what we want to know is what's the degree increased? What's the degree decreased? Okay, so according to Clausius-Krypton equation, equation 6.1-3 and equation 6.5-2, we understand these two equations. According to this equation, we put it together, we can get this equation, which is delta TB here, delta TB here equal to this one. And how about delta Tm? Again, you do the same logic analysis, you will get something like this. Delta Tm will be Tm0 minus Tms equal to RT, the same, right? You just change the symbol here. T is Tm0. For example, for water, that will be 0, right? 0 Celsius, right? Delta H, M will be melting point of latent heat from liquid to solid, or from the solid to the liquid. And again, it's related to the molar fraction of the solvent, of the solute. Right. So here I just want to have a quick practice. Example 6.5-4 colligative properties calculation. So a solution. So here a solution of 5 gram of the solute in 100 gram water is heated slowly to a constant pressure at 1 atm. So you know that the solute you can regard it as sugar. Sugar 5 gram into water 100 gram, and at 1 atm, and is observed to boil at 100.421. So you know the delta T will be what? 0.421. Okay? And estimate the molecular weight of the solute. You want to know, I want you to know, or you need to know what's the material you put into the water. Is it sugar or is it other species? According to you, when you analyze this molecular weight, you can guess what is the material you put into the water, right? And also, the effective solvent vapor pressure at 25 Celsius. Second question. The third question is the solute freezing point, right, at 1 atm. So once you know the X, and it will be easy for you to calculate the rest of them. So the necessary properties of the water can be found in table B1. So in your final exam, if I give you the latent heat of the water, okay, and you need to do the calculation. So according to this equation, in table 1, you know the latent heat of the vapor from the liquid to the vapor will be 40.656 kilojoule per mole. So just put this in here, right? Be careful with the unit. That's what I want to tell you. So you know the delta TB will be 0.421, right? And then you put a gas constant here, you put a TB0 here, okay? So TB0, what is the water? 100 Celsius, right? 100 Celsius, that would be 373.16 Kelvin. And you put a number, you put a latent heat here, and you have an X here. So as a result, you can calculate 0.421 equal to what? 28.5x. Okay. So what is x? So do the quick calculation. What is x? X will be 0.0148 according to this equation. And you understand this is molar fraction. So molar fraction is the molar solute divided by molar solute plus molar solvent, right? And you understand this is 5 grams of the solute in a 100 grams water. So just put this in, rearrange. So the solute, the molecular weight will be 60. So you can have a guess. Why is it 60? What's the species with the molecular weight of 60? Answer, okay? So, and then next question is that effective solvent vapor pressure at 25 Celsius. So as you know, we already know X, right? And then what we need to know is effective. And then effective is 1 minus X here. So we know the X, we know the water vapor pressure. So of course we know the effective at 25 Celsius. Okay, important, the key is what? To find out PS, right? PS at 25. PS 25 is 23.756 millimeter mercury. So effective at 25 Celsius will be this one. Okay? So I want you to do the calculation by yourself. So as you know, 23.4 is lower than 23.756. So that's what we call lowering of the vapor pressure. Okay. And then question 3, solution freezing point at 1 atm. What we need to know is we want to know the delta Tm. Since we know the X, we know the Tm. What is Tm? 0 Celsius, right? 0 Celsius. Gas constant. What you need to know is what? The latent heat of the melting point. At table 1, you got this, and you put the equation in, you put the numbers into this equation, you find delta Tm equal to 1.53 Celsius. And then you know that the TMS will be minus 1.5 Celsius. Okay? I don't have time to do the calculation with you. So please go home, do the practice by yourself. So the summary is the colligative property is the vapor pressure loading, right? Don't worry about these equations. I will give you these equations, but you need to know the definition. So lowering the vapor pressure, increasing the boiling point, decreasing the melting point. Okay? Right. This is the solid liquid phase diagrams. If you put the sugar salt into the liquid, into the water, what happened? This is the diagram. Okay? I don't have time to talk about this, and out of scope in our lecture in the first year, so I will skip this. If you are interested in this topic, please read this by yourself. So next, we will move to 6.6. 6.6 is the topic we have learned before. It's the equilibrium between two liquid phases. I hope you remember if you have, for example, if you have sugar and vinegar together, you will create two phases in liquid phase. And then if you have water and vinegar together, because water and vinegar is miscible, so you will have only one phase. Right? Okay, so miscibility and the distribution coefficient is that what's the degree of the two liquid together? What's the miscibility? So miscibility is that what's the degree? You can form in homogeneous solutions. For example, like water and ethanol are miscible since they are mixed in all proportions. So you can put water and ethanol together, you can mix all proportions. And some of the species, they are partially miscible, like water and MIBK. It's not 100% mixed. As I hope you still remember, we have this example at chapter 4, right? So, and this is example is that so if you create two phases, one liquid phase will be 98% water, 2% MIBK. And another phase will be 97.7% water and 2% MIBK. Sorry, 97.7% MIBK and 2.3% water. And there are some of them immiscible. For example, like this one, water and the diethylene ether. Okay? So what I want to tell you is that this is some of the basic idea is mixable or immiscible. Please read this by yourself. I don't have time. You follow some rules. And in this section, what we mainly want to talk is liquid extraction. I hope you still remember that we already practiced liquid extraction. For example, water, acetone, and chloroform. And water and chloroform acetone was together. And we want to separate this water and acetone. We cannot use distillation because of what? Because these two are, the boiling point is too close and too low. So you cannot do this. So you need to get chloroform. You need to get acetone go to the chloroform. So water acetone is immiscible. Okay, and the water chloroform is immiscible. So water and the chloroform cannot be get together. so it's immiscible. So what you need to know, what you need to do is acetone and the chloroform, right? So this one will go to this place. Okay, so this is the what we call the acetone enter to the chloroform rich phase. And this liquid-liquid interaction, right? Hope you remember this. Right, so we have a kind of distribution coefficient here, partial. This is what we call ABS system. So A is water, B is acetone, S is chloroform, is S, right? And I think you just notice K is the definition of K is this: the X S B in S and B in A. So B in S, B in A. This is what we call distribution coefficient. And this is the table for the distribution coefficient. Okay, you can check this by yourself. This is A, B, and S. And we already practiced this before. We don't have time, so I will skip this. Okay, this is very clear. I want you to know this. Right, I think I want to finish this section first. So please work with me. So, we have ABS, right? So can we, before, instead of checking table, can we use diagram to find out the proportions? This is what we know. This is what we call triangular phase diagram. So again, water, MIBK, acetone, right? Remember this is in chapter 4, water, acetone, and MIBK. And how do you read this? How do you read this? First one is the behavior of the part, blah, blah, blah. It's called triangle phase diagrams. Okay, so let's make, this is the diagram for at temperature 25 Celsius. Okay, and then this is A, which is water, and this is B, which is solute, because acetone dissolved in water, right? It's miscible. And MIBK dissolved the acetone, but not immiscible with water. So this is S, extraction solvent. Okay? And then if you read this one here, this is what we call HB, which line is water and acetone. And this is HCA is here, acetone and MIBK. HC is water and MIBK. So don't try to remember this triangle. I will show you this triangle in your final exam, but I want you to know how to read this. Okay? So this is HB here. And then region A, what is region A? Region A is this part. This is called what we call region A. Is this part. This is called region A. What's region A? Region A is only single phase. According to different proportions of the A, B, S, you have only one single phase. Like this. If you put, for example, if you K point here, if we have a proportion of A molar fraction, B molar fraction, and C and S molar fraction, that will be only one phase. And region B is here. You will have two phases, like this. Like this. You will have two phases. Remember, like liquid interaction, you have two phases. And this phase will be MIBK together with acetone. This phase will be water with acetone. Right? So this region, any proportion, any molar fraction in this region will be two phases. And here will be only one phase. Okay, so let's say if I address K point here. So what's the composition of K point is one phase, right? What's the composition of the water, acetone, and the MIBK in K point? How to read this? How to read this? This is single phase, right? So if I ask what's the molar fraction or what's the weight, I shouldn't say molar fraction, it's the weight percent of the water. This one is, if water is here, right? So you find a line which is parallel, which is the line face to the water. This is a composition here, okay? So this is the line, right? This is line. And line here, 50. So 5, 10, 15, 20, right? So 50 is here. So water is 50%. Okay? K point, the line here parallel to water point here is 50. So what's the acetone? Acetone should be this line, right? Because this is phase to acetone. What's the percentage? Or what's the weight percent here for water, for acetone? 65, right? 65. Okay? So what's the concentration of the MIBK in the K point here? This is what? This line, right? This line is parallel to MIBK, right? What's the percentage here? 20%. 20%. Okay? So if I give you a point in this region, please tell me the percentage of the A, B, and S. Okay? This is case 1. Case 1 is in A region. Right. Okay? So what's the case 2? Case 2, this is K point, right? If I give you a point M here, this is case 2, there are two phases. So you need to know the concentration of this phase and also concentration of this phase. So you have two phases. And in this case, we call tie line. Tie line is this line. It's this line. This is called tie line. You might say, well, professor, if you give me a point like this here, and where is the tie line? The tie line will be here, right? The line between this line and this line will be the tie line. Okay, so let's practice. What is the M? So tie line is between this. Okay, it's called L and N here. And then, because tie line A, L, and N here, right? So for the mixture M point in region B, this total amount, it doesn't matter phase 1 or phase 2. So what's the composition of the water, acetone, and MIBK? Here again, 55. This line will be phase to water, right? 55 here. And how about acetone? This line, right? 15, right? Phase to this one, 15 here. How about MIBK? This line, right? This line, 30. Okay? So the total weight percent of the water, MIBK, and acetone will be 55, 15, and 30. So how about the weight percent of the in the MIBK phase and the weight percent of the in the water phase? And we need to go to the tie line here. Tie line here. L. Okay? What is L here? L point here, right? So the water will be what? Water will be 85. And then so water will be what? This is water rich phase. Water will be 85. And then acetone will be what? Will be between 50 to 10, right? Or between 50 to 10, right? So this is, let's say 12. MIBK will be what? MIBK will be this line, right? MIBK, this line, the phase to here, that'll be 3. So 85, 12, 3, 100%. And how about, this is water rich phase. And this one will be MIBK rich phase, right? MIBK rich phase is the tie line end here. So water will be what? About 5%, right? Let's say, well, here is 4%. Anyway, almost there. And then acetone will be this line, will be what? 20%. And MIBK will be 95 or 96%. If you put these three together, three numbers together, will be 100%. Okay? Right. So that's what I think here is an example. Please, I want you to practice this by yourself. I don't have time. Okay? And I think please practice this by yourself. This is very easy, as long as you find out the point here. Okay? Right. Okay, so I think I finished the section 6.6.